So my name is Craig Hefner. Yay. And obviously, I'm going to be talking about hacking routers today. Specifically, what I'm going to be discussing is how an external attacker can gain access to the internal administrative web interface of your common residential gateway router. Before I start, though, oh, this is the wrong slide set. Damn it. Oh well. Before I start, though, my work did ask me to make a couple statements. First of all, I'm not doing this on behalf of them. I didn't do any research on behalf of them. I'm not here as part of my work, so if you know who I work for, stop calling them and emailing them. But I decided to focus on router security because there's very little security in home routers. I couldn't fit very many screenshots into this slide. I had about 17 more. And all of these vulnerabilities typically are only exploitable from the LAN, because most of them, end up being in the web interface, which typically most people don't have remote administration enabled. So the question for an attacker is not how do I attack these devices and hack them. The question is how do I get access to the device if I'm not on the LAN? And so the answer to that is typically either cross-site request forgery or DNS rebinding. And request forgery is really popular because it's very, very easy to do. But it has a lot of limitations, especially when you're going after routers. So first of all, you can't rely on there being a trust relationship between an internal client's browser and the router, because no one ever logs into their routers. So you can't exploit that. You can't forge basic authentication logins anymore with cross-site request forgery. You used to be able to do, user, password, and then the URL. Yeah, that doesn't work anymore. IE doesn't even recognize that as a valid URL, and Firefox will actually throw a warning to the user. So you can't rely on that either. There's also some anti-cross-site request forgery mechanisms in some routers. This ActionTech router is one, actually, that I'll be demoing later. And ultimately, cross-site request forgery is limited by the same origin policy in the browser, and it always has been. So if you're not familiar with the same origin policy, basically what it says is, okay, if I browse out to attacker.com, I load up some JavaScript from attacker.com. That JavaScript can interact with any page on attacker.com, but it can't interact with google.com or 192.168.1.1. And that's good because you don't want some random person's JavaScript talking to your router. So that's where DNS rebinding comes in. The premise behind DNS rebinding is basically, okay, well, if the browser is going to implement security based on the domain name, that's fine. Just tell it that attacker.com has switched IP addresses to 192.168.1.1. So now when the attacker's JavaScript connects back to attacker.com, the request actually goes to your router. But DNS rebinding has been around for a long, long time. It's like 1996 called and wants this exploit back. It's been around forever. And so people have put in preventions to stop it, or try to stop it anyway. And so browsers have put in patches, and third-party plugins have put in patches. And you also have services and tools like OpenDNS, NoScript, DNSWall, DNSMask also has some anti-rebinding stuff in it. And these all attempt to stop people from using DNS rebinding to attack your internal network. And the way they do that is they say, well, no external domain should resolve to an internal RFC 1918 non-routable IP address. Because if it does, you're probably not going to be able to connect to it anyway. And if they're doing something malicious, then we want to block it. So that's basically how these tools work. So I'm going to focus on using the multiple A record attack, which is one variation of DNS rebinding. And if you're not familiar with it, really all it is DNS load balancing. That's it. You return multiple IP addresses for a DNS lookup. And so pretty much any major site does this. You do a DNS lookup on Google, you get 5 or 6 IPs back. So what happens is the browser says, okay, you have 3 IP addresses. That's fine. And it just tries and connect to each IP address in order. And if one of those IP addresses goes down, that's fine. I've got more IP addresses. It switches over to the next IP address in the list. This attack is limited, though, in that you cannot target internal IP addresses with this. You can target any public IP you want, but you can't go after internal IPs. So let's take a look at using this attack to go after a public server. So you've got your attacker out there with an IP address of 1414, and he wants to send some malicious content to the web server on 2358. Now, he doesn't want his IP address showing up in the logs for whatever reason. So he's going to proxy his requests through this client who's feeling very safe sitting behind his router. So the attackers register the domain name of attacker.com, and he convinces this client to browse out to attacker.com. So the first thing the browser does is a DNS lookup. It says, what's the IP address for attacker.com? So the attacker's DNS server then says, oh, I actually have two IP addresses, 1414 and 2358. Now, 2358 is obviously not the attacker's IP address, but the browser has no way of verifying that. So it just says, okay, you've got two IP addresses, I trust you. So it's going to try the first IP address first, which is 1414, does its GET request to the attacker's server, and the attacker sends back some JavaScript code. Now that JavaScript code then initiates a request back to attacker.com. And the browser says, well, you came from attacker.com, you're going back to attacker.com, fine, that's allowed. But when the browser makes this connection to initiate the request, the attacker server sends back a TCP reset packet. So now the browser says, well, crap, that server's down. I better switch over to the second IP address. And so now the attacker's JavaScript is interacting with the 2358 server. He can send GET requests and get the response back, parse the data, and even send it back to the attacker if he wants. So this works. This has always worked. There's never been anything to stop this from happening. And there's certainly security issues that arise from this. But the real threat has always been attacking the internal LAN. So I don't want to go after some public web server. I want to go after the client's router. I want to get access to the router's internal interface. So this is the same scenario, but instead of attacking a public IP, the attacker is going to try and rebind to 192.168.1.1. So again, client does a DNS lookup. And again, the attacker server sends back two IP addresses. Now, the browser says, oh, you've got two IP addresses. Oh, but one of them is an internal non-routable IP address. And the browser will always try internal non-routable IP addresses first, regardless of the order in the DNS packet. So he's just going to go and send the request to the router and load up the router's web interface in the client's browser. This does the attacker no good because the client never went out to the attacker's web server to get his JavaScript. So the attacker has no presence in the browser. He's accomplished nothing. So the problem here is that everyone's focused on protecting internal IP addresses. Okay? Routers are kind of unique. They have both an internal and an external IP address. And so we can actually attack the external IP address using this method and gain access to the internal interface. And the reason that works is actually kind of interesting. So if you take a look at a netstat on a router, and this is actually from an OpenWRT router, take a look at how it's binding services. These services are bound to every interface on the router. So port 80, yeah, that's bound on your WAN interface. It's listening on the WAN. Now, what prevents just anyone on the internet from connecting into the router are your firewall rules. Now, anyone who's looked at OpenWRT's firewall rules knows this is extremely simplified. But basically it says, okay, ETH0 is my WAN interface. I don't want people connecting in from the WAN. So anything that comes in on ETH0, drop it. Everything else we'll accept because that's our internal interfaces. That's fine. And there's nothing really inherently wrong with this. But like the same origin policy, this attempts to enforce security based on a name. Computers don't work on names. They work on IP addresses. And where this comes back to bite us is when you look at how the underlying operating system handles IP packets. RFC 1122 defines two different models for implementing an IP stack. One's called the strong end system model, and one's called the weak end system model. Now, if you know nothing about these two models other than the names, which one do you think is better? Right. But interestingly enough, the weak model is actually the more prevalent model of the two. It's implemented by Linux, BSD, I believe Solaris, and even pre-Vista Windows. So let's take a look at how this works. This is verbatim from the RFC. You can read it if you want. RFCs are very boring. But all this says is, okay, if I'm a router or any computer, and I receive a packet, I'm going to look at the destination IP of that packet. And if the destination IP matches any of my IP addresses on any of my interfaces, I will accept that packet and process it. Now, it could come in on technically the wrong interface. So it could come in on ETH0 and it matches the IP address on ETH1. Doesn't matter. I'll accept it and process it because obviously this is one of my IP addresses and this packet's intended for me. So let's take a look at how this works in the context of the router. Okay, again, we have an internal client, a router, and the internet. So the router has two interfaces. ETH0 is its public WAN interface, and ETH1 is the internal interface. Now, ETH0 has an IP address of 2358. That's the router's public IP. So what happens when an internal client tries to browse to 2358? Well, he's going to send a TCP SYN packet. And the router's going to look at this and say, well, the destination IP is 2358. That's one of my IP addresses. Awesome. And it goes, okay, the destination port is port 80. Well, hey, guess what? I have a service bound to port 80. Because remember, those services bind to every interface. So he says, yeah, I have a service listening on 2358, port 80, and 2358 is my IP address. So I'll accept this, complete the three-way handshake, and so now the client can actually access the router's internal web interface via the public IP. So, oh, wait a minute. What happened to that firewall rule? Remember, we had a firewall rule that says block everything on ETH0, right? Well, if you take a look at the traffic, the top window is ETH0 and the bottom window is ETH1. No traffic ever went over ETH0. The weak end system model logic happens pre-routing. So everything gets accepted and processed on the internal interface. So that firewall rule that we had that says block everything on ETH0 does nothing because there's no traffic on ETH0. So ultimately, an internal client can punch in the public IP and get the web interface. Now again, this by itself is really not a problem. It's not a vulnerability per se. But I, as an external attacker, can rebind any internal client to any public IP I want, including the router's public IP. So now, if I can do that, I can completely bypass all of these protections that are trying to stop me from rebinding to internal IP addresses, because I'm not rebinding to an internal IP. So let's take another look at our rebinding attack. Again, same scenario as before, but this time, instead of rebinding to 192.168.1.1, attacker's going to rebind to 2358. So internal client does a DNS lookup, and again, the attacker's DNS sends back two IP addresses. The browser looks at that and says, hey, you've got two IPs, they're both public IPs, that's fine, I'll try them in order. Goes out to 1414, gets the attacker's JavaScript. JavaScript initiates connection back to attacker.com, so the browser goes back to 1414 because that's what worked before. But this time, he gets a TCP reset packet back, and so now he immediately switches over to 2358, and now the attacker's JavaScript has full interactive access to the router's internal web interface. So this is a really, really nice attack for DNS rebinding. Because unlike some other DNS rebinding attacks, there's no delay or waiting period before you can rebind. It's pretty much instant. We also don't need to know the router's internal IP address. That's always kind of a problem because, routers can have different internal IPs and people can change the IPs, and we don't care because we're rebinding to the public IP. Another nice thing is this works in all major browsers because this is just how browsers work. It's how they handle DNS redundancy. The downsides are we have some very specific requirements on the router. Okay, we basically have three specific requirements. Okay, the router has to bind its services to the WAN interface. The firewall rules on the router have to block based on interface name and not destination IP or some similar configuration. And the router also has to implement the weak end system model. So obviously not all routers are going to be vulnerable to this. So the question is, which routers are? So I tested 30 different routers, and out of those, 17 were vulnerable. And that includes routers from Asus, Belkin, Dell, which I didn't even know they made routers, but apparently they did. Thomson, these are actually pretty popular over in the UK, pretty popular DSL routers. And one thing I wanted to test, I didn't get a chance, is the BT Home Hub, which is really popular in the UK, and is basically a rebranded Thomson. So those may be vulnerable as well. Lots of Linksys. Lots and lots of Linksys devices. And I really like this slide because the bottom two routers there, the 54GL and the 160, are on Amazon's top 5 most popular selling routers list. So awesome. Of course, a lot of people put third-party firmware on their Linksys routers.